This we have to add 6 to the LSB nibble only. Then this LSB part become 1 plus 1 0 with a carry 1 plus 1 0 plus 1 1 with a carry 1 plus 1 0 with a carry 1 plus 1 0 with a carry 1 0 plus 1 1 is already there, 0 here. So this becomes, say this is 6 and this is 8 illa 4 1 5. So the result is 65 in decimal, which have been 5F in hexadecimal. So this is about rule number 1. Now rule number 2. If there is an auxiliary carry, you have to look into this rule when rule number 1 fail. Rule number 1 states that if any of the nibble is purely hexadecimal, 6 is to be added to it. Even if any of the nibbles are purely not hexadecimal, if there is an auxiliary carry, then 6 must be added to the LSB nibble, where we will not check whether this nibble is purely hexadecimal or not. Even if the LSB is not purely hexadecimal, however, an auxiliary carry is generated while creating the LSB part of the result, then 6 must be added to the LSB part. For example, you consider this operation, addition of 28 with 48. I supply this as, say, decimal numbers. 8 plus 8, 16, that is 6 with a carry 1. 4 plus 3, that is 6. 4 plus 3, that is 7. So we expect 76 decimal as the result. But the processor will perform this as a hexadecimal addition. Addition of 28 hexadecimal with 48 hexadecimal. 8 plus 8, 16. 16 is to be converted into hexadecimal, that is 0 with a carry 1. 16, you have to divide 16 by means of the radix of the number system, 16, which is 1 times with carry here 0. Again you have to divide this by 16. This is 0 times with a carry 1. So the result is 1 0. 1 0 is written as 0 is written here, the first digit, and 1 is taken as a carry. 4 plus 2 plus 1. 4 plus 2, 6 plus 1, 7. You obtain the result as a 7 0. None of the digits in this result is purely hexadecimal. But this is not the exact result. This is in hexadecimal. We are required to convert it into decimal. To do that, we will have to consider the exact operation performed by the microprocessor or the machine. 28 will be loaded to the accumulator as 0 0 1 0. 8 as 1 0 0 0. 4 8 as 0 1 0 0, and 8 is again 1 0 0 0 0 0 and 0. Now we add these two numbers, 0 plus 0 0, 0 plus 0 0, 0 plus 0 0, 1 plus 1 0 with a carry 1. This is an auxiliary carry. 1 plus 0 plus 0, that is 1. 1 plus 0 1, 1 plus 0 1, 0 plus 0 0. This is how you obtain the result 7 0 in the accumulator. Now once we perform decimal adjust accumulator, the first rule fails. None of the bits, nibbles in the result is purely hexadecimal. Then you will have to check whether it satisfies or whether we can apply the second rule. That is, if there is an auxiliary carry, 6 must be added to the LSB. Here we have an auxiliary carry being generated. Then 6 must be added to the LSB part of the result. and there is no question of anything being added to the MSB part, because there is no scope for first rule as well as second rule as long as the MSB part of the result is concerned. So MSB will be 7 itself, and this becomes 0 plus 0, 0, this is 1, this is 1, this is 0, 0, 1, 1, 0, that is 6. This is how 76 decimal result is being generated once you apply this second rule. And the third rule is that if there is a carry, 6 is added to the MSB part of the result, similar to this one. If there is a carry, 6 must be added to the MSB part of the result, even if the MSB is not purely a hexadecimal number. If it is already a hexadecimal number, definitely you will have to add 6 to that number. Even if it is not purely a hexadecimal number, however, a carry is generated upon the generation of the MSB part of the result, then 6 must be added to it. For that, consider this operation: 82 decimal plus 87 decimal. 7 plus 2, 9, 8 plus 8, 16. 6, 9 with 1 carry. The result we expect is 169. But the processor will perform this as a hexadecimal addition. 82 plus 8, 7. 7 plus 2, 9. 8 plus 8, 16. 16 is 0, 1. 1, 0. 1, 0 that I have written here, 1, 0. So this will be the result that we obtain. Now, how exactly this is being performed? 8, 1, 0, 0, 0, 2, that is 0, 0, 1, 0. 8, 7 is 1, 0, 0, 0. 7 is 0, 1, 1, 1. 4, 2, 6, 7. Now we add this 1, 1 plus 1, 0 with a carry 1. 1 plus 0, 1, 1 plus 1, 0 with a carry 1. 1 plus 0 plus 0, 1. 0 plus 0, 0, 0, 0. 1 plus 1, 0 with a carry 1. This result is 1, 0. This is 8 plus 1, 9. 1, 0, 9. This is how this result is being generated. Now you look at the LSB nibble. This is purely a decimal number, not a hexadecimal number. So you cannot apply the first rule. And the MSB part is also purely a decimal number. So the first rule cannot be applied. And for the second rule, there is no scope for second rule because there is no question of any auxiliary carry being generated. So the LSB part will be exactly the same. There is no modification for the LSB part. But if you look at the MSB, though it is not purely hexadecimal, upon generating this MSB part of the result, a carry is being generated. So 6 must be added to the MSB. So here we add 6. This is 9. 0 plus 6, that is 6. And this is 1. So the result is 169. This is how a hexadecimal number is converted into the corresponding decimal number by the microprocessor, and is achieved with the help of the instruction decimal adjust accumulator. However, you cannot perform this operation or execute this statement decimal adjust accumulator whenever you like to perform it. It can be performed only after any one among the 6 basic addition instructions only. So this is about decimal adjust accumulator. Now we consider addition of two 16-bit numbers. Addition of two 16-bit numbers, I mean. So suppose we have the first number being stored in the memory locations with address 8500 and 8501, because basically it's a 16-bit number. There will be a total of 2 different bytes. LSB byte must be saved to a location with smaller address. MSB byte of the number is saved to a location with higher number, higher memory address. So the first number is being stored in the memory locations 8500 and 8501. These are two consecutive memory locations. The second number is stored in the very next consecutive memory locations 8502 and 8503. First byte of second number is stored in 8502. Second byte of second number is stored in 8503. We require the LSB of the result in 8504, second byte of the result in 8505, and there is a scope for a carry also. So the result may be having a third byte. If you are adding to 5 byte numbers, the result can be at most 6 byte because there is only a carry that equal to 1 being generated to the next place. So the result is stored in the locations 8504, 8505 and 8506. Now how this addition can be performed? In order to add two 16-bit numbers, we have this instruction DAA register pair. DAA register pair. In this instruction, content of the HL pair will be added with the content of the register pair whose symbol is mentioned, and the result will be placed in the HL pair. If there is a carry, carry also will be generated. So to add these two 16-bit numbers using DAA instruction, we will have to take the first number to HL pair, and the second number can be taken to any other register pair. Then we may add these two numbers using DAA register pair instruction. Once there is a carry, of course, you might have initialized C register 00. If there occur a carry upon this addition operation being performed, you will have to increment the content of this register C by unity. If there is no carry, content of C might not be incremented. That will be C00. And then the LSB part of the result, or the LS2 least significant bytes of the result present in the HL pair, might be stored to these two consecutive locations. Then you may take the carry content, the third byte of the result or MSB of the result that might have generated in the C register, might be moved to accumulator. Then it must be saved to the location with address 8506. So this is the mode of operation that we have to perform to execute this program. For that, you will have to take 00 to register C. First of all, this is meant for creating the third byte of the result. If a carry is generated upon addition, the content of this register must be incremented by 1. If there is no carry being generated upon performing the relevant addition operation of the program, then the content must be untouched. Content of register C must be untouched. Now we have to take first number from 8500 and 8501 to HL pair. There is an instruction for that, which is LHLD 8500. Upon performing this operation, content of the memory location with address 8500 will be loaded to register L register, and the content of the memory location that is one ahead or greater than that of the address given 8500, which is 8501, that must be loaded to, that will be loaded to H register. So in HL pair, now we have first byte of the first number and second byte of the first number. For first number is loaded to HL pair. Now we have to add the second number to another register. However, there is no direct method of loading any other register other than HL. So we exchange HL pair with DE pair. So the first number is moved to DE pair using this instruction XCHG. Now again we perform LHLD 8502. Then the second number is loaded to DE, again to HL register pair. Now the first number is there in DE register pair, second number is there in HL register pair, we add these two, DAA